Hello, everybody. Welcome back to Markov Processes. I hope you had a good spring break and are ready to get back into it. We have an exam this week on Thursday. You are going to be getting a cheat sheet from me, and I promise you that will come out this evening, so you'll know exactly what you'll have. You will have, for example, the Kolmogorov forward and backward equations, things like that. Yeah, so I want to ask how the homework's going. By the way, just like last time, Wednesday in class will be completely for review, and Wednesday evening, I will have an optional extra review. So yeah, before I ask if you guys have any questions, I wanted to talk about problem 1A on the homework. It's a tedious problem. So we are given a system. We have a biological population, and each individual is assumed to give birth after an exponential amount of time with rate lambda, and to die after an exponential amount of time with rate mu. And in addition, we have individuals immigrating into the population. Let's see. Okay, with a constant rate theta. So we want to show that this is a birth and death process, which involves writing all that long stuff out, unfortunately, and showing that we have the little o stuff and we have the lambda I and the mu I, right? We want to write out the probability that xt plus h minus xt is 1. So that's the probability we increase the population size by 1. Given the population size is currently I, we want to get some kind of lambda I, which we're going to define, times h plus little o of h. And we want to go down by 1 and get some kind of mu I h plus little o of h, where we have to define mu I. So mu is the death rate per individual, but mu I is the death rate for the entire population. Right? So if everyone is racing to die, then there's going to be an overall death sooner than there's going to be an individual death for most people. So that's going to happen faster. And we want to have a change of 0 with probability, 1 minus lambda I plus mu I h plus little o of h. And you don't have to go through all of these. It asks you only to go through this one in 2 different cases. When the population size is less than n people, at which time there's immigration into the system, or greater than or equal to n people, at which time there's no immigration. So I'm just going to look at A and get us going here. So I'm going to assume that the current number of people in the population, that's what we start with, is less than n. So we do have immigration. And if I look at the probability that xt plus h minus xt is 1, given xt is I, then this says we have a net increase of 1 in our population in an interval of length h. And because we're going to the definition of a birth and death process, which has these little o definitions, we want to be thinking h is small, h is small, h is small. So what could happen here is, I'm going to write this kind of, I hope this notation will make sense. To increase the population size by 1 in this interval of length h, we need 1 birth and 0 deaths and 0 immigration. And this is all conditioned on the current population size being I, but I'm not going to write it because this line will get kind of long. Or we can have 0 births, 0 deaths, and 1 immigration. Again, given that xt is I. Or we can have 1 birth, 1 death, and 1 immigration for a net increase of 1. Or we could potentially have like 3 births and 2 deaths and no immigration. But for each individual input stream, we've got the birth stream and the death stream and the immigration stream. The probability of getting two or more events in a tiny time interval as we let h get small is little o of h. So I'm going to just tie the rest up in a little o of h term. So this takes care of a whole bunch of terms like 3 births, 2 deaths, and 0 immigration, because each individual stream can't have more than one thing happen in this tiny time interval. So again, all of this is conditioned on the population size being I at time t. And so we're going to need to figure these probabilities out. The streams are assumed to be independent, as they always are in this course. I don't know if I said it, but I would have had to give you some sort of dependence. Like if they're not independent, then how are they dependent? So these are independent. And that means we get to break these probabilities up. 1 birth times the probability of 0 deaths times the probability of 0 immigrations plus, and then, we'll get another term and the little o. So let's just look at this one. If we have I people in the population, we need to choose one to give birth. And we need to know the success probability for this binomial, because what we have is we want to see how many births are in there. We want exactly 1 birth. We have I chances. We have I individuals, each of which could give birth. And so if we want to have exactly 1 birth out of I individuals, we need to choose 1 to give birth. And we need to choose the remaining I minus 1 to not give birth. And that's a binomial thing. So we're going to need the success probability, success meaning an individual gives birth in this tiny time interval. So yeah, this is not complete, but I'm going to let like a little p be the probability any one individual gives birth in the interval t to t plus h. Each person gives birth after an exponential amount of time with rate lambda, a constant rate lambda. Okay, so the probability that one individual gives birth in that interval, we're looking at the process at time t, and it doesn't matter that they've already been waiting to give birth. The lack of memory property says that this is the probability that the birth time for that one individual is less than or equal to h. So this is the probability that t is less than or equal to h, where t is one of these exponential rate lambda birth times. And this, because it's exponential rate lambda, is the CDF. This is 1 minus e to the minus lambda h. And if you know what this is, we're going to try to mash everything into this little o form. So I'm going to start right now with that. You could use this in this bigger calculation, and then eventually you would smash it into little o form. But this is 1 minus the Taylor series expansion here for e to the negative lambda h is 1 minus lambda h plus 1/2 lambda h squared minus 1 over 3 factorial, to make it look the same, lambda h cubed plus. So the ones cancel, we get lambda h, and the rest of the terms have h to the power 2 or higher, and those are all little o of h. So this is the probability any one individual gives birth in that time interval. And let's go back to what we were trying to do. We want to look at the probability that the overall population in this interval of length h increases by 1, given the overall population is currently I. And we rewrote it as 3 things. And we're currently looking at this thing. So this is the probability of 1 birth and 0 deaths and 0 immigration. And we said that these streams are independent. So we get to multiply. For 1 birth, out of the I people in the population, we need to choose 1 to give birth. The probability any one gives birth, so that's like success versus failure, is lambda h plus little o of h. So we get that to the 1, and we get the rest of the probability, 1 minus lambda h plus little o of h, to the I minus 1. And let me color code this. This is this. This problem is quite tedious, unfortunately. I think the rest of it is not. The rest of the assignment, much less tedious. So I need to multiply it by the 0 death probability. And I currently have I people in the population. So if each individual will die after an exponential amount of time with rate mu, then if you want to find the probability that any one individual dies in that interval, this is going to look the same, but you're going to have mu's instead of lambdas, and you're going to end up with a mu h plus little o of h. So now out of I people, I want to choose 0 to die. I've got the probability that any one dies in an interval of length h being mu h plus little o of h. I get that to the 0. I get the rest of the probability to the I minus 0. And so that is the second piece of the first of 3 terms in this process. So now we have 0 immigration to take care of. You get a different color. I know the pink, not so great in showing up. But this one, I don't know if it's easily differentiated. But in the immigration stream. So this is a constant Poisson process. People do not really immigrate well, there's kind of a dependence on the population size being above n or below n. But we are in the case where the population size, the current population size is less than n. And so we've got a Poisson stream coming in. And so this is going to be, the term I'm about to write is the probability of 0 arrivals in a Poisson process with rate theta in an interval of length h. This is going to be e to the minus lambda h to the 0 over 0 factorial. So that is one term out of the 3 we need. And although we've done some little
was it theta for the Poisson part?
Oh, thank you so much. Yeah, this Poisson is in terms of theta, not lambda. Yeah, so what I was just saying was that we did some little O of H simplification, but there are more to be done when you start multiplying these things together. And there's 2 more terms. So there's a lot more to do for part A. I am really tempted to say, don't bother with B, but I'm sure a lot of you did it already. So I'll make B some number of bonus points because it's just more tediousness. But we've got these 3 things, and we have to add another product of 3 things and another product of 3 things, and you just have to mash through it. And here's what to expect. So I know what the answer is going to be to part A. And this is really what's going on in C. In C, you're just asked to make an argument for what the birth and death parameters are without the little o stuff. So lambda I solved my problems. Lambda I is the birth rate. Okay, this is maybe a misnomer. I'm not talking about individuals giving birth. It is the rate of increase of the population of size, an increase of size 1 when the current population is I. And that could come from an immigration, not a literal birth in the population. So this is the overall birth rate, which includes, it's just increasing by 1, which includes immigration. And if I is less than n, when is the next birth? So we have these I people, and we have a constant stream here. So this person will give birth after an exponential amount of time with rate lambda. And this person will give birth after an exponential amount of time with rate lambda. And if I have I people in there, the next, like, I'm using the word birth in 2 different ways. The next birth in this population is the minimum. So the next birth time is the minimum of I exponentials, each with rate lambda. That time is exponential with rate I times lambda, because the minimum of, say, n exponentials with rate lambda we saw is exponential with rate n lambda. But those aren't the only things racing, because the next increase of size 1 of this population could actually be from immigration. And the immigration process is independent of what's going on in that circle or that blob. So I want to look at the minimum of like a T1 and a T2, where T1 is exponential with rate theta, and T2 is exponential with rate I lambda. So I took I exponentials and made them into 1. And then we have to compare it also with this. If the immigration comes first, that's how the population size increases. And the minimum of 2 exponentials has another exponential distribution, assuming they're independent, with rate equal to the sum of the rates. So that's when the next event will happen, the next increase event. So going back up to the birth rate, this should be I times lambda plus theta. This is like a I different exponentials with rate lambda racing and throwing in another exponential with rate theta to the race. Yeah, what we have when there's currently I is we have 1, 2, 3, down to I, 1 person, 2 persons, down to I persons. This one will give birth after, I'm going to change my notation, after an exponential amount of time with rate T1. This one will give birth exponential amount of time with rate T2, Ti. And then we also have the immigration, which will be after an exponential amount of time, say with rate T. So these are exponential rate lambda all the way down to here. And this is exponential with rate mu, with rate theta, because it's a Poisson process with rate theta. So these are all the different ways that we can have an increase. We can have person 1 give birth, or person 2 give birth up to person I, or we can have an immigration. So when is the time that the population increases by 1? It's whatever happens first out of those I plus 1 things. And we're comparing I exponentials with different rates. And the minimum of, I'm sorry, I plus 1. And the minimum of those is exponential with rate equal to the sum of the rates. So if you sum up all these rates, you have I times lambda, and then you have another theta here. So you get I lambda plus theta. A long time ago, we had, we had some IID exponentials with rate lambda. And we let y be the minimum of these exponentials. And we wanted the distribution for y. So we were looking at the CDF for y. This is the probability that y is less than or equal to y. This is the probability that the minimum of x1 through xn is less than or equal to y. And we wanted to rewrite this probability in terms of the individual x's because we know their distribution. So I put like a y on a number line, and we wanted to figure out how the individual x's must fall so that the minimum is less than or equal to y. And there are many ways for that to happen. So we turned the probability around. We took a complement, and we had 1 minus the probability. The minimum of x1 through xn is greater than y. Because if you want the data to fall in some way so that the minimum is greater than y, that's equivalent to them all being greater than y. So this was 1 minus the probability that x1 was greater than y and x2 was greater than y, out through xn being greater than y. And these were independent. So we get to multiply. And each of them has the same PDF. So yeah, yeah, so this is 1 minus those tail probabilities, or 1 minus the probability x1 is greater than y to the n, and that is 1 minus e to the minus lambda y to the n, and that is 1 minus e to the minus n lambda y, and that is the CDF of an exponential with rate n lambda. But in the birth and death stuff, we have usually I people, not n. And yeah, we could also show using the same kind of technique, ending here. If they're not the same exponential, then we wouldn't get the same probability to the nth power. What we would get is something like 1 minus a tail probability for one exponential times a tail probability for another exponential out through another tail probability, which is going to be 1 minus e to the minus lambda 1 plus lambda 2 plus lambda n times y. And so the minimum here, this is the CDF of an exponential with rate lambda 1 plus lambda 2 plus out through lambda n, which jives with what we have up here, because if all of those are lambdas, then that sum is n lambda. But that's why we're allowed to combine the lambdas exponentials with the thetas exponentials. We get to add the rates. I was trying to do 1C, and this was reason out the birth rates. So if there's I people in the population, the time that the rate of increase is going to be I exponentials with rate lambda racing, and that is a minimum, and that is another exponential with rate I times lambda, and that also races with the extra exponential with rate theta. So the minimum of an exponential I lambda and an exponential theta is exponential with rate I lambda plus theta, and that holds for I less than n. And then when I is greater than or equal to n, we just have the I lambda. There's no immigration. Mu I, so mu 0 is supposed to be the death rate in the population when there's currently 0 and there's no one there to die. There's just no death rate going on. And we're in the case where we just kind of want to reason this out. So if there's I people in the population, then we have I exponentials with rate mu all racing to die. And that means the time of the next death is the minimum of I exponentials, each with rate mu, and that is exponential with rate I times mu. And that actually holds when I is 0, so this is going to hold for all I. This is what I'm asking also on the review, where it says, like, just reason your way through it. Don't write out all the tedious stuff. There's only one more thing that's on the exam, and that's the stationary distribution we got to at the end last time, and that is totally formulaic, super easy. So I want to derive that formula today. I don't know if I should just go to the example. Now we can do examples if I don't get to today. We can do 8 million examples on Wednesday. So let me derive that birth and death process formula. Let me know if I've scrolled up enough. Okay, we want to find a stationary distribution for a birth and death process. So what we have is a generic birth and death process. We have a birth and death process with birth and death rates given by lambda I and mu I. And I want to talk about stationary and or limiting distributions. So a stationary distribution is going to be a pi, and it will have a discrete looking subscript because there's a discrete, the y-axis is discrete here. It's the population size. And it is stationary if it's equal to Actually, we usually say pi j is equal to the sum over I of pi I p I j. But because pi j actually now depends on time, the stationary equation now has an of t in it. And this has to hold for all t and for all I in the state space. That's our new stationary equation. We had a theorem, and this was called continuous time Markov chain T1 for theorem 1. And this equation is not something you want to be solving because the p's are changing in time, so it can be very complicated. But we had this idea of a generator matrix, and we said in this theorem, and we proved that the vector of pi's is stationary if and only if pi times the generator matrix Q is the row vector of zeros. So the generator matrix is filled with things like lambdas and mu's and maybe 2 lambdas and 3 lambdas and things like that. So this is something you could solve to find pi. But in the interest of time, I'm just going to state a fact. For a nice birth and death process, and what I mean by nice is something pretty technical, but essentially the rates are such that the process is not, the population is not going to blow up. So you've got some births and deaths. And if the birth rate is too fast compared to the death rate, then this population size is just going to go off to infinity. And it's not going to make sense to talk about a limiting distribution or even a stationary distribution, because if you have a certain distribution of, the probability you're in state 0 or 1 or 2 or 3 or 4 on up at time t, at a later time, you will tend to be higher up if your birth rates are too fast when related to your death rates. So we're going to see exactly what I mean by this when we solve for some stationary distributions, but for a nice birth and death process, when the rates are amenable to there being an equilibrium, the limits, we can show the limit as t goes to infinity of the probability of going from I to j in t units of time. We can show that this exists and they are independent of I. So I guess I should say exist in the singular. The limits exist if the birth and death rates can kind of balance. And so I'm going to call the limit pi. This is just like what we did in the discrete time case, and it should be independent of I. So this should be some notation that depends on j, and I'm going to call it pi j. In the case that this limit exists and is independent of the starting value I. So this, just like it was in the discrete time case, is stationary. Let's look at our new version of the stationary equation. I'm going to start with the right side. I'm going to sum over all I, pi I, p I j of t. And what I would like to see is pi j, if it's going to be stationary. So I'm going to replace the definition of pi I with this, well, with its definition, this limit. So this is going to be the sum over I, the limit as t goes to infinity of pij of t. No, not true at all. Pi j, this has to match this. And that means that if I'm writing pi I want to go to I. Oops. I want to go to I from an arbitrary point that doesn't matter. So let's say pki of t, and k is irrelevant. And then pij t. So I just replaced pi I with a limit, and the limit is the probability of moving from any place to I in t units of time as t goes to infinity. So you know the drill, we interchange things sum over I, P, K, I, T, P, I, J. What the heck? I did the same mistake here. T is fixed over here. And so pi I should not have the limit in t. I should take it in a different time step. I'm going to make it like time s. It's going to infinity, so I don't want it to be the particular t that is sitting over here, which is finite. Okay, so let me fix that down here. This is s and s. And this is of t. And here I've got a Chapman-Kolmogorov equation. So I have the limit as s goes to infinity. So this thing I put an under bracket on takes us from state k to state j in s plus t units of time, running through an intermediate state I that we summed out. So this is the Chapman-Kolmogorov equation, and this is the probability of going from k to j in s plus t units of time. So s is going to infinity, and it doesn't matter that we already started at time t. This whole argument is just going off to infinity. The t is kind of irrelevant here, and this is how we defined ij. So we have it. I started with the right-hand side of the stationary equation and got the left-hand side from the limit, which is pretty darn cool if you ask me. Right now, I want to derive that formula that we had that I threw in at the very end last time of the stationary distribution for a birth and death process. And I'm going to derive it using the Kolmogorov either backward or forward equations. I think that forward may be a little nicer. So consider the Kolmogorov forward equations. That was P prime of t equals P of t times the generator matrix Q. And the ijth entry is Pij prime of t, and the sum over, say, k of Pik of t, so that's going across the ith row, and then Qkj. So that's the ijth entry of the Kolmogorov forward equations. I want to use this to find the stationary distribution, to find the pi's for the birth and death process. And in the birth and death process, like so many others, a lot of the q's are 0. So we have qi, I plus 1. That is the rate of increase of birth at the time the population size is currently I. So that is lambda I. And we have qi, I minus 1. That corresponds to a death when we're starting with I. And that death rate is going to be mu I. So I've started with a birth and death process with given birth and death rates, lambda I and mu I. And we can go from I to I. And that is going to be the diagonal entry for the generator matrix. That's going to be the negative of lambda I plus mu I. And then Qij is going to be 0 for j not equal to I minus 1, I, or I plus 1 for all the other cases. So that means that only 3 terms are going to survive here. Actually, it'll be a little different in the case when j equals 0. So let's look at j equals 0. I want to write this out using this information. And I'm just going to write it in the interest of time. The probability of going from 1 to 0 in time t, the derivative of that with respect to t, that one actually only has 2 surviving terms. And this, if you work it out, should be negative lambda naught Pi0 of t plus mu1 Pi1 of t. So that is me plugging in 0 here, plugging in 0 here, realizing there's only 2 rates that go to 0 because the death rate, mu0 is 0. So this is what you will get from this equation if you plug this in when I is 0. Actually, when k is 0. Does that make sense? Even if you couldn't follow that, you understand what I'm doing. I'm just like evaluating this expression. Okay, so let's assume you believe that. I am going to take the limit as t goes to infinity on both sides here. Now, these are going to the pi's. That's how we define the pi's. And if these probabilities are going to a constant, then derivatives of these types of probabilities are going to 0. So if this is going to a constant, that means that Pij0t prime is going to 0. So when I take the limit all the way across this equation as t goes to infinity, on the left side, I get 0. On the right side, I get negative lambda naught pi 0 plus mu1 pi 1. And if I solve for pi 1, at least in terms of pi 0, we'll get that pi 1 is lambda naught over lambda 1 pi 0. So there is an expression for pi 1 in terms of pi 0. Yeah, so let's look at this Kolmogorov forward equation in the case where j is greater than or equal to 1. If j is greater than or equal to 1, the Kolmogorov forward equation becomes Pij prime of t equals, this is going to be lambda j minus 1 pi to j minus 1 of t minus lambda j plus mu j Pij of t plus mu j plus 1 p I to j plus 1 of t. Let me go back up. I am writing this equation for a, I'm letting j be anything greater than 1 because the 0 case is a little bit different. I have qkj, and so the non-zero terms, given that the j is fixed, the non-zero terms come from qj minus 1j, qjj, and qj plus 1j. The qj minus 1j is a birth when the population size is currently j minus 1. So that is lambda j minus 1. The qj plus 1j is a death when the population size is currently j plus 1. So this is mu j plus 1. And the jj, that's the diagonal term, is the negative of the birth rate when there's j in the population plus the death rate when there's j in the population. So I use those 3 q's and the big sum I had in order to write down the Kolmogorov forward equation in the case when j is greater than or equal to 1. And now I'm going to take the limit as t goes to infinity, and the limit of these is how we define the pi's. And if all of those are going to constants, then the derivative is going to 0. So the left side, this limit is going to be 0. And we end up with 0 equals lambda j minus 1 pi j minus 1 minus lambda j plus mu j pi j plus mu j plus 1 pi j plus 1. This is for all j greater than or equal to 1. Let's look at j equals 1. We get 0 equals lambda 0 pi 0 minus lambda 1 plus mu 1 pi 1 plus mu 2 pi 2. And we know that pi 1 is lambda naught over mu 1 pi 0. So if you plug that in, you have an equation with just pi 0 and pi 2 in it. And you could solve it in the interest of time. I'm just going to spoil this. You'll get, when you solve for pi 2 in terms of pi 0, you'll get lambda 0, lambda 1 over mu 1, mu 2, pi 0. If you looked at this equation when j equals 2, that would pop out a pi 3. And if you wrote the pi 2 in terms of pi 0, and so you had an equation with just a pi 3 and pi 0s, you would get pi 3 equals lambda naught, lambda 1, up to lambda 2 over mu 1, mu 2, mu 3, pi 0. And your guess for the general pi n is going to be lambda naught, lambda 1 up through lambda n minus 1 over mu 1, mu 2 up through mu n times pi 0. And we can prove that formally with induction. If you're comfortable with induction, it's extremely straightforward. There's no tricks here, but it is a little tedious. So you could also conclude that with a ... argument if you write out enough of these and see the pattern. But that's how we get to the formula I gave you at the end last time for the stationary distribution for a birth and death process. And that corresponds to a limiting distribution. And all of these only really exist if the birth and death process is nice. And that will be built in. You don't have to worry about that. I'll show you where you will figure out that the stationary distribution does not exist. Let's do an example. So this is the example I did at the very end, and I did it completely out of context. So I'd like to give a little more context right now. This is something known as an MM1 queue. So we're just starting to get into queuing. A queue is, queuing is the science of waiting in line. And when you have an MM1 queue, this means, so the 1 means there is one server. And what's happening is you have an input stream, you have a server, and then people leave. And you could think of the picture this way. Let me move this a little bit. You have a person at the server in service, and then the rest of the people kind of lining up back here. And the M's here stand for memoryless. The first M is saying that the inter-arrival times have the lack of memory property, and that means they're exponential. The second M is saying that the service time, it also has the memoryless or lack of memory property, and that means it's exponential. And they each have to have some rate. So let me just, this bullet thing is kind of not cutting it right now. This means there's one server. This means that the inter-arrival times are IID exponential with some rate, say rate lambda, could be whatever you want to call it. And the service times are IID exponential with some other rate that I'm going to call mu. So people are coming in. So this is how it's usually drawn. An arrow with a lambda, they're coming in with rate lambda, and then they're being served with rate mu, and then they're leaving. This, if you let xt be the total number of customers here in the system. What do I mean by that? Let me just finish this at time t. This is the people waiting in line and the person in service. So this includes the person in service. The picture I drew back here looks like there are 3 people in the system. This is how you define an MM1 queuing process. And this is a birth and death process. The population will go up and down. And in an infinitesimal interval of time, it'll go up by 1 at most, or down by 1 at most. And if we can write down the birth and death rates, we can use our new exciting formula to figure out the stationary distribution for the total number of people in the system. So let's do it. Yeah,
Okay.
it is. It's like we're decreasing the population by 1. So let's write down the birth and death rates. If there's no one there, the next person is coming along according to a Poisson process. I didn't say that, but I said exponential inter-arrival times, and that's equivalent to the Poisson process. So the next person is coming in with rate lambda. Same thing if there's currently 1 in the quote unquote population, the arrival rate is still lambda. No matter how many people are there, people are coming in at a constant rate. So we get that the birth rates lambda I are lambda for all I equals 0, 1, 2 on up. We could show this the long way with the little o stuff, but as you know, we need to move past that. That is super tedious. So I'm doing it the reasoning your way through the rates way. So let me know if that doesn't make sense. The death rates, if there's 0 people in the system, then no one is departing. So there's no rate of departure. If there's 1 person in the system, then it looks like this. Like there's no one in line. There's 1 person here. That person is being served with an exponential amount of time with rate mu. And the time of the next departure happens after that exponential amount of time with rate mu. So the death rate is just a constant mu, or at least when the population size is 1. And if the population size is 2, that corresponds to a picture with 2 people in the system. But because there's only 1 server, we don't have 2 people racing. If we had 2 servers, each exponential with rate mu, the next departure from the system will be the minimum of those 2 exponentials. And now we're talking about racing exponentials. But here, the time to the next departure is still exponential with rate mu. And if there's 3 people in the system, the next departure is going to be this person, and that will be after an exponential amount of time with rate mu. And so we get that mu I is 0 or mu. It's going to be 0 if I equals 0, and it's going to be mu otherwise. So constant birth rates, constant death rates. Let's go to the formula that we just derived. So I want to find the stationary distribution for the number of customers in this queue when it reaches that sort of equilibrium, when it reaches either a limit or it reaches a stationary mode. So if this is a server and you are opening a store in the morning and you have 18 people already in line, it's not starting in stationary mode. You're going to have a big long line, but eventually it will kind of settle down and reach an equilibrium. So that's what I'm looking for. The way I would ask this would be find the stationary distribution for the number of customers in the system. That includes the person in service in equilibrium. When I say that, I mean like it has settled down and it has reached its stationary mode or its limiting distribution. This is a pi problem, and we have an exciting new formula. If you kind of remember this formula and kind of don't. Note that you should never have a mu 0 in the denominator because mu 0 is always 0, and that's going to cause problems. Okay, so all of the lambdas are just lambda, and all of the mu's are just mu. So this is the same thing as having lambda times lambda times lambda times n of those and n mu's. So we get lambda over mu to the n times pi 0. So I do not have pi n yet. It's in terms of pi 0. We need to find pi 0. And to find pi 0, you just need to use the fact that we need all the pi's to add up to 1. So the sum from 0 to infinity of pi n needs to be 1. And that's a constraint that will allow us to find pi 0. Let me back up one line and say that this holds for n equals 0, 1, 2 on up. It's only guaranteed to hold for 1, 2 on up. It is a formula for n greater than or equal to 1, but just by observation, if I plugged in n equals 0, that would give this coefficient would be 1. And so we'd have pi 0 equals pi 0, and it holds. But you will not always, this formula is not always going to hold when n is 0. So, right, if you somehow, I'm totally changing this. This is wrong. Don't write this down. If you somehow ended up with n minus 1 here, then if you plugged in 0 on the left, you would have pi 0 equals lambda over mu to the -1 times pi 0. And that does not hold unless lambda over mu equals 1. So this formula does not always hold when n is 0, but it does in this case. Okay, so I'm going to say that 1 is equal to the sum as n goes from 0 to infinity of pi n. And we have a formula, 0 to infinity, lambda over mu to the n times pi 0. And I'm going to pull that constant pi 0 out. And we have something that looks like a geometric sum. But yeah, we could get in trouble if the birth rate is larger than the death rate. This will converge only if the lambda over mu is less than 1. It's like an r to the n, and the magnitude of r has to be less than 1. And for rates, these are never negative, so we don't really have to think about the absolute value. This is saying we need lambda less than mu, and lambda was the rate of input, and mu is the rate of service. And if people are not being served fast enough relative to how fast they're coming in, the line is going to blow up, and the number of customers at infinity is going to be infinity. And also in terms of stationarity, if you picture a histogram sideways at some time step, the histograms are going to be kind of rising because the customers are going to be increasing. So this is a condition for the MM1 queue to have a stationary distribution. And yeah, let's add this up. So we have 1 equals pi 0, and I'm going to do that geometric sum. It's 1 over 1 minus lambda over mu. And this implies that pi 0 is 1 minus lambda over mu. And pi n, therefore, was lambda over mu to the n times pi 0. And this holds when n is 0, 1, 2 on up, because you can check when you plug in 0, you do get this back. Sometimes, again, these formulas will only hold when n is 1, 2, 3 on up. So we have found the stationary distribution, and this only happens if the arrival rate is smaller than the service rate. So that's a constraint for the problem. And you recognize it. It's a geometric distribution. It's a little weirder than we're used to seeing, but remember, if x is geometric, the one that starts from 0 with parameter p, the probability that x equals x is 1 minus p to the x times p. And the expected value of X is 1 minus P over P. And so if I make like a part B to this problem, what is the expected number of customers in the system in equilibrium? You can just use this result from the geometric distribution. So the expected number of customers in the system, this includes the person being served, in equilibrium. That means that even though you started with a massive group of people outside your store in the morning, it has leveled out. This is, oh yeah, I should have said here that the number of customers in this equilibrium is the geometric starting from 0, and P is actually 1 minus lambda over mu. So the expected value is 1 minus lambda over mu over 1 minus lambda over mu, which is lambda over mu over 1 minus lambda over mu. And to get rid of those fractions, I'm going to multiply the top and bottom by mu. This is lambda over mu minus lambda. And fortunately, that denominator makes sense because we did have to assume that lambda was less than mu. So I don't have a 0 in the denominator and I don't have a negative expected number of customers. One more question here, and you won't have to do these sorts of things on the exam. At most, you'll go to this. You'll see on the review problems. But I want to put a part C here. What the heck? I'm going to put a part C. The expected number of customers waiting when the system is in equilibrium. So we found the expected number of customers in the entire system, and that includes the one in service. So this should just be the lambda over mu minus lambda minus 1. And if you compute that, you'll get mu over mu minus lambda. So, yay. We haven't officially started queuing yet, but one of our examples of a birth and death process was a queue. And we know some things about it. Okay, so if everybody is okay, let's look at the machine problem that's like problems 3 and 4 or 2 and 3 on the homework, but just a tiny bit different. So another example of finding a stationary distribution by first recognizing something as a birth and death process. So I've got one of these machine problems, and it's either operating or in repair. And I'm going to let X of t be, I think I did this the opposite way on one of the homework problems. That's why I said this is just like it. I'm going to let it be 1 if the machine is operating at time t, and 0 if the machine is in repair at time t. And I want to try to find a stationary distribution here. It will not exist if when you are trying to find pi 0 by summing and setting it equal to 1, if that sum does not converge, then the distribution doesn't exist. So this is, well, there's a couple things we can do. I'm just going to write method 1, but not take the time to do it. Method 1 would be to write a generator matrix. Oh, I haven't given you anything about how this progresses. So let's suppose that the operating times are IID exponential with some rate. I'm going to be leading here. I'm going to say rate mu and not lambda, so that when we turn it into a birth and death process, things will be in the right place. But I would not be adverse to changing it up to make sure you are thinking about the problem you're solving. And suppose that repair times are IID exponential with rate lambda. I could hide what I meant by having like a rate, I don't know, using completely different Greek letters here. So 0, 1, 0, 1, and 0 in this case is operating. 0 is in repair. So if I'm in repair, then I will move to operating after an exponential amount of time with rate lambda. And that means the rate of moving from 0 to 1 is lambda. And the row has to sum to 0, so this is negative lambda. Okay, so if I'm in state 1, and that means that the machine is operating, it will move down to state 0 after the machine stops operating, and it will operate for an exponential amount of time with rate mu. So mu is the rate of moving from 1 down to 0. And then the other entry has to be negative mu. So we could solve pi times q equals 0. Now pi here will only have a pi 0 and a pi 1. If you'd like to stretch this out to have all the pi's, you could have a generator matrix with lots of zeros in it. You will only end up being able to find a pi 0 and pi 1. And you want to solve this subject to pi 0 plus pi 1 having to be 1. So we could do that, but my method 2 is going to be to think of this as a birth and death process. This is a birth and death process. The birth rate, when there are 0 people in the system, there's no people at all. But, you know, when the population size is 0, when the state is 0, we're thinking of the states as a population size. The rate of increase by 1 when the machine is in state 0 is lambda. The rate of increase by 1 if the machine is in state 1, the machine cannot go up to state 2. There is no state 2. So this is going to be 0. And the others would be 0. If the population size, there's no population, is 0, we should have a death rate of 0. This is the rate for our example of going from state 0 down to state -1, and it doesn't happen. So the rate we consider to be 0. If we're currently in state 1, we will go down to 0 with rate mu. So it's a restricted birth and death process, and you can include again all the other states as long as you say this, lambda 1 is 0. That means you can't get up to 2, so you never have to consider values 2 or greater. Okay, so I am almost out of time, but I want to use our handy dandy new formula. And so pi 1 is lambda 0 over mu 1 pi 0, and this is lambda over mu pi 0. As soon as you go up to pi 2, you're going to get a lambda 1, which is 0. So the ratio is going to 0 out. And let's solve for pi 0. Pi 0 plus pi 1 has to be 1. This is pi 0 plus lambda over mu pi 0 is 1. This is 1 minus lambda over mu plus pi 0 being 1. And this tells us that pi 0 is 1 over 1 plus lambda over mu. And if I multiply everything by mu, this is mu over mu plus lambda. And then finally, pi 1 is 1 minus pi 0, which gives us the rest of this fraction, lambda over mu plus lambda. And that's what you should get with method 1. So you might want to check that if you want some practice. But the long run time, proportion of time the machine is working means we're in state 1, is lambda over mu plus lambda. And the long run proportion of time we're in repair is mu over, no, I did it the other way around, but whatever, I'm out of time. Yeah, operating is 1. So yeah, this is the long run proportion of time we're operating. I'm out of time. As usual, I have some time to stick around because I suspect there's more homework questions. But otherwise, I will see you next time on Markov processes.
Wellness and immunity support. It's designed for allergy sufferers like Allie. She often felt tired and run down. Then she added Allerlife Energize, a unique blend of vitamins and herbs for immune support. Plus caffeine, it helps put a pep in her step. Allerlife for life. Let's walk.